I'm going to do this motion worksheet 2 here. With all these solution videos, if you felt really, really good about the homework, you should go ahead and scrub through this, like fast forward and just check the answers. And you don't have to watch the whole thing if you don't need to. On the other hand, if you feel like you want to hear your physics teacher, that's me, hi, if you want to hear me talking about this and going through the problems, then that's what I'm going to do. All right, so I got here, consider the position versus time. This is a position versus time graph for two cars. So just thinking about what these graphs, what information we have here. As time goes by here from 0 to 15 seconds, this car right here, its position is increasing, and this car right here, as time goes by, its position is decreasing. Okay, so let's see. In 1, describe the motion of car A. Use complete sentences. Oh, geez, I don't know about that. We'll see how I do with that. Before I do that, actually, I'm going to go ahead and find, I know that I'm going to need the slope and the intercepts of these lines. So the intercept, just look at the graph here. That looks like that's at 15. And the slope of this one, let's see, rise over run. So I'm just going to use the points that are the furthest apart here. Farthest apart? Furthest apart? That's 75. So it looks like my rise, I'm going from 15 to 75. So for car A, right here next to where it says car A, the slope is 75 minus 15 is 60 meters. That's my rise over 15 seconds. And if I divide that out, that gives me 4 meters every 1 second. All right, that's going to come in very handy. And then here for car B, what's the slope of this position versus time motion graph? Looks like I'm going from 10 down to negative 35. So from 10 down to negative 35, that is a rise of negative 45, and that's also 15 seconds. So that looks like negative 3 meters over 1 second. Okay, so I think I can use these numbers. The reason I just wanted to do that first is if I want to really be totally descriptive of what's going on, I think those numbers can come in handy here. So describe the motion of car A. If you say what the slope and the intercept are, like put that into a complete sentence about it, I think that that's going to get everything, right? So I'm going to say car A starts at position, I'm going to call this position X. I'm imagining that they're going back and forth on a number line, right? Moving on like a number line road. So I'm going to call those positions X. You could say position. Starts at X equals 15 meters. That's the y-intercept. And moves in the positive direction at 4 meters every second. All right. I think that's a pretty complete sentence. I use some symbols there, but that's fine. So, complete sentence. How about that? Let's see if I can say the same thing for this. So, car B starts at position 10 meters and moves in the negative direction. Does that mean it's going backwards? What do you think? No, just going the other way. Doesn't mean like if you're driving on Route 11, like let's say from the high school up toward Walmart there, and you look across and you see cars going the other way. Well, you could imagine Route 11 as like a number line, right, where there's things going in pretty much one-dimensional motion up and down Route 11. Those cars that are on the other side going south, like from Walmart to the high school, they're not going backwards, they're just going the other way. And who's to say that's the negative direction? Well, I mean, somebody's got to decide if we're going to start doing math about it. So we might want to say that high school toward Walmart, that's a positive direction because that's north, and maybe that seems like it should be positive, but you could decide the other way. Just have to be consistent. Car B starts at that and moves in the negative direction at 3 meters every second. It would be redundant and really kind of wrong to say that it moves in the negative direction at negative 3 meters every second. You just have to mention the direction one time. So you could say it moves at negative 3 meters every second, or you can say it moves in the negative direction at 3 meters per second. If you say it twice, then you've got that like two negatives canceling each other out kind of situation going on. What is the speed of car A? The speed, that is the absolute value, does not care about direction. So the speed of car A is 4 meters per second, because that is the slope of the position versus time graph. Because that's what my physics teacher said. What is the speed of car B? How do you know? The speed of car B is the absolute value of its velocity. The speed of it is 3 meters per second. If you included the negative here, it's not a huge deal, but speed, the speedometer in this car ain't going to say negative, right? You need to just have the number part of that. The speed is 3 meters per second. How do I know? Let's say this is the absolute value of the slope of position versus time. In which direction is each car traveling? The car A, positive direction. Car B, in the negative direction. How do you know? The sine of the slope tells us the direction. I think there's other things you could say there too that are perfectly fine. You could just say, like, looking at the graph, the positions of car A are increasing and the positions of car B are decreasing. That would be a perfectly reasonable and correct thing to say there. Where does each one of the cars start? Car A starts at 15 meters and car B starts at 10 meters. How do you know? Again, there's different things you could say here that would be correct. You could say that's what their y-intercepts are. You could say that. You could say these are their positions at time 0. I mean, look at the graph, right? Time 0. And there's the positions. Write the position equation, the x equals v times t plus initial position for each car. To keep them straight, I'm going to do this. Got a paper under here. I just poked a hole in my paper. So the position for car A is equal to, and then for position for car B, I'm going to write them like that. So for car A, its v is 4 meters per second. You have to include these units. This is just like equation writing we did in Unit 1. That's why we did all that, to get ready for writing real physics equations. 4 meters per second times time plus the starting position, which was 15 meters for that car. Super important that you include the units on both of those. Again, this is like a y equals mx plus b. You can be thinking that, you just can't write y equals mx plus b. So for car B, its velocity here, we're including the sign because we need it to have we're really writing the equation for this line as a negative slope, times time plus its initial position. What will the position of car A be at 50 seconds? Show the calculation. Well, I've got a position function now for this, so the position car A at 50 seconds. If you want to, I'm just going to scribble that out for a sec. I want to rewrite that. The position of car A, you could write this like you do in math class, where this is like f of x. This is the thing I'm going to plug in. This is like position at time this. You could do that, and I would be okay if you left that out also. So let's see, is 4 meters per second times time plus 15 meters. I write these out sometimes. When I start to do the algebra here, I leave the units out. So now position of car A is equal to 4 times 50 plus 15. And I just remember I'm going to get an answer that's in meters when I'm done. That looks like it's going to be 215 meters. And for car B, I've got a position function for that one too. So B at 50 seconds is going to be negative 3 meters per second times 50 seconds plus 10 meters. And notice how the units do exactly what we would need them to do, right? They cancel out. I get negative 150 meters plus 10 meters is negative 140 meters. Great. That's it.